the YouTube video about how this is speeding, and I said that I will skip this program last time. Now I can show you now. It's very interesting results here that you can use my program. Okay, I can guarantee you that my program won't rise to anything. Okay, you can feel safe in using it. My program is doing one thing. I'll read the partition table in the first few, first matters, right? 512 bytes of the air hard disk. So what is a hard disk? You know, I forgot to bring a hard disk. Okay, I know that not many students here know what is a hard disk. Okay, next time I bring a floppy as well. Okay, so how many of you don't know what is a floppy? Huh? Okay, bring a floppy. Okay, floppy is an FAT12 processor. Okay, so without a number, that means the entire hard disk. With a number, that means a particular partition. So you will see that when I use the df command is a command to show all the disks that's attached to your system. So you will see I actually have two hard disks. One is the SDA, one is SDP in my Linux downstairs in my office. And in the Linux system, it not just mount every physical hard disk, but it will create some virtual hard disk. So there's a virtual hard disk. You will see something called 10 MFS. Okay, some is none, some is a U device. Okay, if I have time, I will talk about all this kind of virtual file system. And this is the physical file system. The physical file system, you will find the numbers here. SDA 1, 2, 3, 4. Okay, some of them I didn't mount it. Okay, so whenever you find this, it means a partition. So if you're still confused, what is a hard disk or a partition? So an entire hard disk is like this. A partition is this small box. Okay, so some of the hard disks will, I don't know why. Okay, but some of the automatic partition tools will leave some space between some partition. Okay, it doesn't matter. It doesn't mean that, oh, I have a space is better, I don't have a space. It doesn't matter. Okay, you can always change it in order to remove those spaces. It's up to you. But whenever you mount one of the partition, you will create a number. In Linux, you will find an SDA1, SDA2, and in a partition table, it's only 4 slots. Okay, so you can find my partitions here. One is equitable, yeah, something that you don't understand. Okay, but it doesn't matter. I'll just tell you about this. And if you read something else which is wrong, let's say I read SDA1. SDA1 is a partition, not a hard disk. So inside a partition, you won't find a partition table. So what it will find? It will find something irrelevant. Okay, it will find something irrelevant. If you point to a partition, but you point to a hard disk, I choose SDP this time. I have 2 hard disks in my Linux machine. You will see I have one partition, not bootable, a huge size there, and you can find which is this one. Okay? Yeah, which is this one. The size here is not a byte. Okay, it's block calculation. Okay, so it's a little bit strange here, but you will find in my SDP only one partition, and in my SDA I have 4. Okay, so this just show you some examples about what exactly is a partition and how to read it. And last time we talked about this guy. So the head you will see is moving with some strange sound. Okay, and whenever it's moved, okay, it will be positioned with what we call a track or some specific term, we call it a cylinder. Okay, so usually we call it cylinder. And when a head moves to that particular track, it will keep on spinning and reading this area. Okay, so we usually call this sequential access. So the hard disk will do a sequential access. Whenever, let's say that you are having a huge file, let's say a DVD. Okay, a DVD, you put it, sorry, it's about some illegal act, right? You rip a DVD, put it in your hard disk, illegal, right? You rip a hard disk, put it there, and then you try to start with the first track, you read it, and suddenly you find out, oh, this boring, I want to skip to the last track. Then you will find some delay there. It's actually, we position the head to the track you want, and then start the read again. But usually when you write to the hard disk, the data will be usually written in a sequential way. It's usually not requirement, okay? When you write to the hard disk, usually in a sequential sense, so whenever you read a DVD, you seldom hear your hard disk moving the head around, okay? And this is all because of a design of the file system. If the file system designed in the sense that it is not sequentially written, then you will have a problem, okay? And what is the problem? The problem is this area, okay? This area. This is just happened to be a image, okay? So this area, the head motor cannot move too fast, okay? Yeah, around less than 200 times per second. So it is a very slow device compared to the bandwidth that's supported by the SATA channel, okay? So this is some background that you need to know because it will also be echo later in the design of the FAT file system, design of some basic file system that you will see. And whenever you talk about formatting a disk, it means you're creating a file system. And the file system usually has a rigid format. What is a rigid format? Let's say you reserve some of the space, which cannot be changed for a particular area, particular information, and other area for another particular information. Okay? So there is some restrictions there, like the extent 3, extent 4. They have very interesting restriction. The restriction, I can give you an example. How many years before? Those guys, we call it, when is this guy graduate? That graduate is 2009, okay? So while he is doing his FYP, I'm not his supervisor, and he asked me one question. The question is very interesting. It's about what I just tell you. Some fixed area for storing something, some fixed area for doing something. Okay, so let me tell you what are the fixed area. One of the fixed area is to store how many files are in your system. Every file allocates some bytes, okay? So area to store the files. And other areas store the file's content, okay? So his FYP is doing this, email spam filter, okay? So what is the characteristic of an email spam filter? You have to store many emails, okay? In order to know what kind of spam you will have, right? Let's say you have a style A, style B, up to a style 1 million, okay? So you will have found many files. And what is the characteristic of an email? Small, very small, okay? So what is the characteristic? When I generalize it, I would say that the ratio to the number of files is kind of equal to a 1-to-1 ratio to the data that we need. We have one file, then we will have one data item or data block. Unlike a DVD file. DVD file, you have one file but a huge allocation area. Keep this in mind. Later on, I will continue this joke. This joke is very interesting. Let me tell you what is the consequence. The consequence is he find that his FIP cannot go on. Yeah, his supervisor cannot help him. And even I start with a stunned face and I say, hee, certain rights, okay. Then what is the problem? His problem is he find that he still has this space, but cannot write any file. The file system always says that this is full, but he knows that he has many space. Okay, he just saved 1 million email there, and each email only 1K, and he has a 500 G hard disk. He cannot go on. Later, I will keep on telling you about this story. Okay, this story is very interesting. Okay, so we will go for, if you go to elite class to audit the course, continue audit the course, we will find a third form of allocation. I will talk about two forms of allocation in the regular lecture. The first is usually we call it contiguous or continuous, or up to you, you choose the adjective, okay? So to continuously allocate things in a hard disk. So where can you find a continuous allocation? You will always find it, I forgot to print again. How many of you have seen what is a cassette tape? Yeah, this test of time, okay? Test how old are you? Wow, wow. Don't pretend, okay? Don't pretend to be young. Yeah, cassette. Let's see, I spelled it wrong. Huh? I'm young. Huh? Cassette tape. How many of you have seen this? How many of you have owned it? Ah, nice, 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 nice. Very good, very good. So, yeah, that anything else you can. Huh? If you're listening to a song 1, you want to go to song 12, what should you do? Fast forward for how many times? We don't know, right? You have to inspect the content again, and then, oh, I reached 12 songs, then I continue to play. Okay? It actually happened in some file system. Okay? And to your surprise, that file system you are still using. Okay? Continuous allocation is about cassette tape. So what is it? I give an example to start with. Think of a book. Okay? A book is actually a continuous, expect you to read continuously. Alright? And that's why the data content, that is a chapter, is allocated continuously. You won't expect there is a book that page 1 is chapter 1, page 2 is chapter 11. Right? That is a random allocation, right? It's a series of chapters, and it's allocated in a continuous manner. Okay, and with the content itself, it doesn't make any sense for a book. A book, we need a table of content, right? What is a table of content? Table of content is an index, right? It's an index to tell you that how many chapters we have. When we map it back to our file system, it means how many files we have, right? Now think about it. How do you know how big is a chapter in a book? How big is a chapter? I mean, count not by words, okay, by page, number of page. How can you count it? Just addition, subtraction, whatever you want to say, right? You do some subtraction, and then you know the distance between the chapter 2 and chapter 1. Then you know how big is chapter 1, right? File system is just like this, right? Let's imagine that if you are writing a book, you are doing this. How about writing a file to a hard disk and you follow the book style? You allocate the first data block, as if I call it chapter 1. You start with the address number 1, and you continue to write it until you know the end of the file is reached. Then you will start another file. I will consider it as another chapter, maybe a chapter 2. You only allocate 1 page to that file number 1. File number 2, then allocate more pages, continuously allocating 9 pages. Then you will continue with another. Okay? So the index page is missing. I don't talk about index page. The table of content is very important now. It guides you to a particular location in order to pick up that file. Right? If I pick out this table of content, we totally lost track of how many files we have. How can you allocate the next file? We don't know, okay? So that's why we have the table of content, and in a file system, we don't call it table of content. How can we call it? We call it the, I missed the keyword, here, the root directory, okay? The table of content is actually the root directory. Okay, let's say in a chapter you have sub-chapter, that means sections. Then it will be subdirectory. Okay, you do it continuously. Of course, the layout of the table of content is a little bit different from root directory. The root directory usually for ease of storage, ease of information retrieval, we will save the name, save the starting address. Together we save the size. Okay, we seldom based on the size and do the calculations. Okay. And with this support, with this size support, then we can introduce holes between 2 files. Understand what I mean? In a book, you won't expect that there are holes, that means blank pages in between two chapters, right? You expect that, oh, page 1, you say that is a chapter 1, then chapter 2 start with page 2, and chapter 3 start with page 10. It means page 9 is still for chapter 2. So you won't expect there are holes. And in file system, we will usually support that kind of host. That's why I will also, I run out of battery. I forgot to charge it. Okay, let me use this. Okay. Okay. Oh, CHK stuff is sucks. Sucks. All right. So I'm, I don't care whether the battery is belong to me or not. I will take the faculty things and plug in my own device. Yeah, you recorded, so I will replace it back, okay? Yeah, good. All right, so where am I? You? Yeah, just like that, okay? I'm getting old, right? I talk about the gap there, right? The gap between two files, huh? So you can see in this allocation, you will find hosts, right? From address 100 to 1900, and the next file start not from 1901, but there is a hole. Usually we support that. For a file system, you don't expect that a file system is always continuously allocating, right? There may be holes there, and we support it. All right. So now this is maybe a brand new thing or idea, right? Table of content is root directory. Okay. And then what? Let's say that I don't draw the holes, okay, too complicated for me, okay? So I just write down some big hole there. And when you map this table of content or root directory back to the layout here, you will find something like this. What is the characteristic? The characteristic, first of all, you won't find a file broken into pieces, scattering around the hard disk. Okay, imagine that this is a hard disk allocation area. It's always packed together. And now you understand that the hard disk is not just for data. Where is the table of content, right? You don't say that, oh, I saved some files, okay, but I lost the table of content. Yeah, it doesn't make any sense. When you save some file or you want to delete some file, you will store and update, I don't know what an operation, add, remove, modify, okay, all happen as a part of the hard disk. So the hard disk will store the table of content, the root directory, as well as all the file content. Now, this may be the first time you say this. Remember, last time I already mentioned this, metadata goes to directory. I'm doing the same thing here. Metadata, this is the metadata, goes to the directory. But those metadata may not be interesting to LS, right? LS don't care about the starting address. You are the implementation, you are the code, okay? You are the implementation of the file system submodule in the kernel. Then this makes sense. To LS won't show it, right? LS is just responsible to show the address, the size, and the file name, right? As well as there are maybe more metadata, but here, this example is a minimal set of example here. I don't show too much details. Maybe you can also think of, oh, where is the modification time? Where is the creation time? It can all be stored in this table of content, but what you need to do is to make it bigger. Okay? So everything fits my previous illustration, the previous set of slides. We talk about this entry in the root directory is an array, right? Fixed content, fixed width. I have fixed content every time I have 3 items: name, starting address, size. Every files you can create a structure and call it directories entry structure, and we have 3 structure here written as an array. All right? So everything fits. What are not fitting in is the operations. We look at operations now. Okay? So any question about the standing part? Standing part is okay. Yeah, just a book. Operations. Operation number 1, add the file. Delete the file. What else? Add a file, delete a file, grow a file, right? Maybe change the file. Can we all support this kind of operations? Grow, change, add, delete. Let's think about how we implement this for. The easiest one is deletion. Yeah, deletion is always easiest. I said that deletion means that I only last slide, update the directory. Okay, don't need to update the data point. So what is the meaning? Now very clear to you. I just update the table of content, cross out that entry. By crossing out, I'm not doing something lazy. Maybe I try to update the whole structure and move this to be the second entry. Okay. So how can you manage the free space now? Still okay. I can manage some free space. The free space will be starting from 1900s plus 1, okay, to 4999 bytes. Okay, so free space management, but you need to calculate, but who cares, okay? As long as I can manage the free space, that's okay. How about the deletion process? Is it fast? Very fast. I just delete it. I don't care the things inside of this. Just put it there. But no one knows its exists. No one knows. Because you lost the handle to it. Okay, I removed the handle. So this is easiest. So I said that there are at least 4 operations I want to support. Add, remove, grow the files, shrink the file. Now, do you think that shrinking the file is something hard to do? Shrinking is easy, right? You just change the file size. I mean, the shrinking may be a little bit hard. Let's say I want to remove the first byte. Remove the first byte is a disaster. Big O of n processing. N means n number of bytes, right? You don't understand what I mean? Think about it. You want to remove 1 byte. How many bytes you need to move? The entire file, right? Yeah, so it's hard, but you can avoid, right? Every file system has this problem, okay? You have so happen that naughty guy want to add some bytes to the first byte, then I have to shift all the data to the right by 1 byte, or you want to delete the first byte, shift it to the left. Very hard, okay, but very easy to understand and also implementable in this file system. In this file system, how growth? File growth. What do you think? Do you have any problem of file growth? Let me go back 1 slide. Tell me, what happens if I want to grow rock.mp3? Wow. I want to grow rock.mp3. Don't tell me that my file system don't support growth. Yeah, who use it? Okay. What should you do if you want to grow rock.mp3? I think you will think of 2 ways. One is obvious. Any idea? Jason, any idea?
Just
add to the end, but here, how come I add to the end if I don't have any space? Move the file after it, the sweet.pbg. Okay, so move for, let's say, 1K, okay, to make space. Good. But that means that when you try to add the content, you involve a lot of disaccess. Okay, which is not good, okay? And later I can also show you some bad examples. Okay, any other ideas? Whoever think of break the file into 2 parts? No, yeah, you already seen that there's no way. How can I implement it if you want to support it? I want to break it into 2 parts. Yes?
You remove the original file and then put the new file at the very end.
Another possibility. Okay, good. So move this guy to the end and let it grow. Good. But here you have to update many entries. But not a lot of problems, still workable. Okay. So it seems that no one will agree to break it into 2 parts. Okay. You agree? But how can you do it?
Can we find the empty space large enough and put the growing part there and we add a pointer from the original
Linked implementation. Right? Implement a linked list on hard disk. Yeah, you ever think of it? Hard disk linked list? Yes, there is a linked list file system. Let me fast forward a bit. Really, you are very advanced. Okay, we actually have this kind of implementation, but you need extra support. Okay, but well, back to this example, two feasible, more feasible linked list. We'll put it later. Two feasible solution. Let it grow, but move the guy that's blocking away to anywhere you find a big enough hole, or you don't want to grow, but copy my target to the end of the hard disk and just let it grow. Okay, both works, but both involve a lot of hard disk access. Now, let me show you impossible file operations. I mean, possible, but not always happen. Is adding a new file like this. Can you edit? Can you find a hole that is big enough? You cannot find a hole which is big enough, but what is the free space available? The free space is enough for the Ubuntu.iso, but there is no such a hole. What should you do? What should you do? Tell me. What are you going to do? Huh? Move. Yeah, then move. How do you move it? Move which hole? Which hole? The first hole. Move this hole. So that means you pack all the allocated space together. Okay? Yeah. Somebody already have a hot debate because you may have heard of this. Do you know what's this operation? It's the name. Huh? Some old enough guy should know about this. Huh? Yes, Chinese name is correct. What is the English name? I don't. The English name is I don't know. Okay. Defragmentar, right? This defragmentation. Yeah. So what is a fragment? Fragment means something broken, right? And fragments here, well, we should say that fragment is the allocated space. The allocated space is now broken into fragments. So you want to pack all the fragments into one piece, so that you didn't change the allocations. The allocation of the hard disk is still the same. The free space are still the same, but now you have to big enough hole. Okay? How many of you never heard of this? Yeah, because I am older than you, right? This is a sad truth, okay? I am older than you, it hurts. Okay. Yeah, let me put up a Windows. Yeah, Windows has these tools, don't worry, yeah? Yeah, if you, I don't know for Windows 7, Windows 8 and Windows 10, I don't know whether it exists or not. XP must have. 7, let me see. 7 should have. Yeah, should have. Huh? 7 should have, yeah. 8, I don't know. And we have 8 here. Please, later on, we find the same tools together. Hey, what happened? Windows sucks, huh? Put up. Oh, come on, baby. Yeah. Good to you, okay? Yes, don't respond. Okay, now. It's like magic word. All right. So should be in accessories. No? System tools. System tools. Yeah. This defragmentar. Yeah, we have this. So does it mean that FAT radio or NDFS has this problem? They have a different point of view over what should be done to that defragmentation. But in our talk here, our focus on the defragmentation means I want to create a big enough hole. And in FAT32 and NDFS, they also face this problem, They also face this problem, but their way to solve it is to break the file into parts. Okay? And later on, I tell you why we need defragmentar. If I break into parts, doesn't make any sense, right? It's already a break into parts, and I guarantee that you have ways to read it back. But why we need it. Later on we talk about it. But in this file system, we definitely need it because we cannot find a hole. And there is a name for this problem. We call it external fermentation. Okay, external fermentation. External fermentation means that we have the total space which is available for our request, but we cannot find such an allocation space. The total space is okay, but I cannot find that allocation space for my request. Okay, this is external fermentation. Later I will show you internal one, where it's internal fermentation problem. And this problem is very troublesome. You have to put everything together, move all the blocks, to make that hole big enough. So I will give a thumb down to this kind of operations involving the moving of the disk. Okay, the creation bad, field-based management still bad because why? Whenever I create a new blocks, my worst case is to update the entire hard disk. Okay, and you calculate the free space management again, and again. Okay, and well, so many bad things in one file system. And you know that file system, of course, I'm not talking about a cassette tape. The cassette tape, usually when you buy a cassette tape, you won't throw that song, right? You won't shame that song. You seldom delete that song, and that's also you don't have the table of content. But for file system, there exists. It's this guy. ISO 9660, Microsoft Unix file system, they both implement that way. And they're only, the best performance for this file system appear on read-only media, the best. So whenever you face the read-only media, you won't face any problem about growing, shrinking, creation. You never have heard of it, you can delete a file from CD-ROM, right? Okay, so whenever it's read-only, and we know that we won't change the content anymore, this is a very good file system or very high performance thing. Okay, the thing about this is only about the seeking of data. Okay, you have sensed that. Okay, how many of you still have a CD-ROM and using? Yeah, I have CD-ROM, but I never use. Okay, okay. So whenever you change, let's say you read something and change it another thing, do you sense some sound as well as delay? Yes. Okay, everybody ask him to give you a show. Ask him to give you a show. Yeah. Read something, and while you're reading one file, you jump to another file, you sense that there is a delay as well as some strange noise from your CD-ROM. It's not something rubbing about CD-ROM, okay? Your CD-ROM damage, okay? It's repositioning, but whenever it is repositioned finished, when repositioning finished, it will give you a very high speed access because it's sequential. It's sequential. It's reading. It's sequential. Okay. I forgot to bring a CD. Okay. You can find I hope that you still have some CD or DVD-R. You can find that whenever you write something, okay, it will write from the inner side and to the outer. Maybe I asked the wrong question, okay? How many of you have used CD or DVD read-write media? Good, okay? So turn to the back. If you didn't write to the full capacity, turn to the back, you'll find two different colors. One is darker, one is lighter, okay? So this shows you that when you write to the disk, it's actually just like this allocation, but in a radial manner. It's a radial manner. It's just writing in circle and circle and circle and going outward, okay? So it needs to be positioned and then use laser to read the content, but very fast. Much faster. If you compare to a cassette tape, it's like that. Yeah, cassette tape you have to use a I don't know whether you tried it. Use a pencil, spin it. Okay. Nobody seen it. No problem. Yesterday. Yeah. Yeah, Apple Data is good to me. Know that I will teach this. Yeah, the cassette tape, okay? Yeah, can you see this? He is using a pen to insert to it and then spin it in order to seek to that file location. Seek, okay? This is the file seek, okay? Yeah, manual file seeking. If you're interested, go to read it. Yesterday, it's yesterday news article. Okay? Good. So you kind of understand, this so easy implementation, very trivial implementation is really put in the deployment and still exists. I don't know from when, okay? Because the first CD I own is already 1990. Yeah, 1990. 25 years ago, I owned my first CD. It's still there. Okay, the file system still exists. Okay, and it's still working fine because of the read-only media. Okay, now think about it. I don't know whether you have heard this experience. This may be a invariant thing. Okay, in your mind. Okay, I have a trial. Okay, I buy a CD-R or DVD-R. Okay, I want to erase some file. Or erase some file. Will this space come back to you? No. No, this space won't come back to you. And what it's doing is actually just update this. But cannot release all what are the things that already written in the disk. Okay? And of course, when it's updated, it just crosses out to market or just laser burn it away, okay? Yeah, so this is a very straightforward implementation. Any question you want to ask about this sequential or continuous allocation really happening? If you don't understand it, buy a cassette tape and play it for a while, then you understand it. Okay. Good. Linkless. Linkless is something that's still using. It exists in FAT series. FAT series and FAT 12, FAT 16, FAT 32 expects, okay, as well as NEFS. They are all using linkless implementation, and our classmates already hints at what is linkless. You want to write to a hole, but the hole is not big enough. Why don't we break it into 2 parts and use the linkless to remember the allocation? Okay? So how to build this linkless? We try to reverse the game. Okay, the game already talked about in the continuous allocation is to allocate things continuously. Now I say that no, it is not a requirement. Okay, so what is the linked list? The linked list is, first of all, okay, we won't say that at random location I will break the file into 2 parts. No, okay. In this manner, okay, we cannot position, we can, okay. What I want to say is we cannot position to a specific byte and read that specific byte. I should say that we usually position a specific byte and read a data trunk, a big enough trunk, maybe 1 megabyte, 2 megabyte together, starting from that byte, okay. And this design is actually take advantage of this hard disk physical design. You are spinning, right? Why not we just let it spin and create a minimal allocation, which is not just 1 byte, but several trunks, big enough block size, okay? With a faster spinning turn, we can have bigger blocks. But nowadays, most file systems support the minimal 1K, okay? If it is floppy is a 512 byte size of this block. Let's take a look at my VM. My VM treat 1 box as a, okay. So how can we test a block? Very easy, yeah. Create a test file, okay, and write 1 byte in. Save it. Properties. Good. What is the block size? Okay. it just chops the hard disk into pieces. Whenever you want to allocate 1 byte, and we take advantage of the spinning of the hard disk, we say that you are not just allocating 1 byte for the file. I will give you that whole block to the file, and that block depends on the time. By the time you format the hard disk, you can say that, wow, I format hard disk, I make it into 32 bytes block, no problem. Okay? And here is a 4K block. Later on, I will give you this engineering problem. What is the engineering problem? The engineering problem is whether we should keep the block small or keep the block big. Yeah. We can have a block 512 bytes, or we can have a block 32 max. What is the pros and cons? This is an engineering problem. Later on, we'll talk about it. All right. So let's continue with the English, and we break it into 2 parts. Okay. So where can we store the linked list information? Yeah, the best place should be the root directory, right? I break it into 2 parts, and I tell the directory that, yeah, it's broken in 2, okay? You are the kernel subsystem. When you read that file, please don't forget about these 2 little trunks, okay? Now, how can we implement that linked list allocation in the root directory? Now, this is the linked list allocation on this area, physical data area. How about this area? We have to support it. And there are solutions. Do you like this solution? Yeah, I set up several layers. I said that for root directory, it is just an array of structures. Okay, so I want to pack it into a regular look. Okay, although the the first item rock.mp3 is not broken into pieces as a linked list, I will allocate 1 guy here and leave these 2 guys now. And how about the latest Ubuntu.ISO? I break it in 2 parts. The first linked list is from address number 9 to address number 26. And then the second piece is 34 to 35. Do you like this allocation? Or can you find any limitation? Any limitation? I don't talk about this performance, okay? Let's forget about performance. Any limitation if I implement a file system like this? Yeah, if you look ahead, you will see. Okay, don't look ahead the slide.
There will be many unnecessary blocks.
So you say this guys?
Yes.
So some unnecessary, so bigger with directory. Okay. So any other limitation? No.
If a file has many blocks,
Many pieces, many fragments. Okay, so that means this file system only supports three separate chunks, 3 separate area, right? So this is the limitation. You see the limitation? You cannot, let's say this file, okay, 8 trunks here, 8 trunks. Original design, the original idea, not the design. My original idea is I can break it into linked lists. That means that I can break this guy into 8 separate area. I put 1 guy here, 1 guy there, 8 different area. Okay. Can I support this? No. The root directory is not wide enough. It's not big enough. Then you will say that, oh, then make this root directory into 8. How about I have 1,000 fragments? I have 2,000 fragments. I have 1 million fragments. You can support that, right? You will have a problem that you don't know how big the root directory should be. So what should you do? There are 2 proposals. Okay, I give you the first proposal, the beginning, and then we will end this lecture, and you tell me whether it's good or not. The proposal is like this: borrow 4 bytes from every blocks. Borrow 4 bytes. Yeah, that 4 bytes is not considered as a data trunk. Okay, and each 4 bytes will store just the next pointer, right? I store my next pointer, but the next pointer is not a pointer, but a block address. Okay, So this guy will be saving 1, and next pointer will save 2. You save 2, and this pointer is 3, so on and so forth. Okay? And of course, this is a linked list. I will put a null 0 at the end. Okay? Linked list, okay? This is a linked list. Yeah, I'm implementing a linked list. I brought 4 bytes, and 4 bytes to represent an address. Tell me whether it's good or not, okay? We will see tonight. Yeah, I know it's disaster.